Hi everyone. So this will actually be our last lesson of the year. We're just going to kind of recap everything that we've talked about with graphing sinusoidal functions and wrap up by doing some applications. Now, before we get started, I would make sure you have out a calculator, ideally a graphing calculator, but it does not need to be one. And then I think that might actually be it. So, like I said, we're going to talk about some applications. So we're going to do two different ones. So the first one has to deal with a Ferris wheel. And now if you think about a sinusoidal function, so it's just something really that just keeps, it's an ongoing cycle. So if you think about a Ferris wheel, once you get on the Ferris wheel, you go up to the top, down to the lowest point, and then just keep going on and on if you were to stay in that Ferris wheel. So here it says you are riding a Ferris wheel with a diameter of 40 feet. When the last seat is filled and the ride begins, your seat is approximately 4 o'clock. The following equation can be used to model your height above ground as a function of time in seconds. So I actually went ahead and graphed this in Desmos. So I'm going to pull this up. So here's another, well, it's kind of intimidating, another way to look at this. Oh, and I can stretch it out. Perfect. So we get in the Ferris wheel over here at 0 seconds. On our way up to the top, we hit that maximum point, so the very top of the Ferris wheel, and then we're going to come down to the bottom. And then obviously, so an actual Ferris wheel goes around in a circle, but this would really just be the height you are from the ground. So the y-axis would represent the height from the ground, and then the x-axis would represent the time in seconds if we were to graph this. So before we get started, I want you to make sure that your calculator is in actually radians mode. So typically we were using it in degree mode, but we want it back in radians. So if you just go to hit mode, radian, so mine already is actually set in radians. If yours is not, make sure that you highlight that and just hit enter so that it's dark. Okay, so now that we took care of that, also just a recap here. So keep in mind, a few things that we're really going to pay attention to. This 20 in front is our amplitude. And then this plus 23 at the very end would be that sinusoidal axis or vertical shift here. So part A says, what is the lowest you will go as the wheel turns? So the lowest is referring to our minimum. So kind of like if you were asked to figure out the range, we would take the sinusoidal axis, so I'm going to abbreviate SA, and subtract the amplitude. So when I do this, my sinusoidal axis is 23, I subtract 20, and I get a minimum of 3 feet. So the lowest you will be on that Ferris wheel is 3 feet off the ground. Let's see if we can see that on the graph as well. So it looks like we're going up by 2 units or 2 feet, each box on the y-axis. So here is the minimum, and we can see that that's at 3 feet. Next up, what is the highest you will go as the wheel turns? So this is going to be referring to our maximum. So this time we're going to take the sinusoidal axis and add the amplitude. So if I take 23 plus 20, I get a maximum of 43 feet. And you can see that on the graph as well, up here at our maximum. Part C, this is where we're going to need our calculator. So at what height are you at after 9 seconds? So they told us that T was seconds. So I'm just going to substitute 9 into my function. So I'm going to do this actually directly into my calculator. So I have 20 cosine. That pi over 4 I'm going to put in parentheses. So in parentheses, pi is above your exponent key over 4. Close that out. And then another set of parentheses. So I want to substitute 9 in for t. So 9 minus 3, or you could put 6. Now notice I want to take the cosine of all of this. So I need one more closed parentheses to finish that out. And then plus 23. So here I actually get 23 feet. And then let's see if we can see this on Desmos as well. So I'm going to find 9 seconds. So it's right here whoops, sorry, right over here. And then here we go. Whoops, I had it a second ago. So I'm trying to do it with my cursor, but it might be easier with or my pen, but it might be easier with a cursor. So hopefully you could see that, there we go, 9 seconds, 23 feet. Okay, D, how long does it take to make one revolution around the Ferris wheel? So this is the period. Anytime we're talking about one revolution, one cycle, that's the period of the function. So remember, to do this, we do 2 pi divided by b, and that b is the number right after sine or cosine, but before our variable. So b in this case is pi over 4. So if I wanted to take 2 pi divided by pi over 4, remember with fractions, instead of dividing by a fraction, you want to multiply by the reciprocal. So I'm going to do 2 pi times the reciprocal, so 4 over pi. So I can put this over 1 to make it a fraction. The pi's cancel out, so I'm left with 2 times 4, which is 8. So it's 8 seconds for one revolution. That seems a little fast there. And I'm going to skip the average rate of change for right now. So that's something we've talked about earlier this year, but I don't think we're going to do with this particular question. So I'm going to do one more in case you'd like to see another example. If you think you have enough information right now, that's fine as well. So San Diego, California is a gorgeous part of the world. Whether it's summer or winter, you want to be there. But what if you're someone who likes long sunny days? When is the best time to go there? Assume that the following formula gives you the number of hours of daylight in San Diego when you input any day of the year, letting T be the day of the year from 1 to 365. You can figure the number of hours of sunlight, or H, if you enter a value for T in the equation. So part A says, what is the average number of hours of daylight throughout the year in San Diego? Now, think about if we were to graph this, kind of like we did with this Ferris wheel. The average is right in the middle there, right in between your minimum, your maximum. What's kind of that? Right in the middle. This is really just our sinusoidal axis. So anytime you see the word average, we're most likely talking about the sinusoidal axis. The one thing that I do want to point out here is it's throughout the entire year. So we'll see another question, I think, that talks about average, or sometimes they might talk about just the average for 1 month, but this is the entire year. So looking at our equation here, it looks like the sinusoidal axis located at the very end here is 12. So there's 12 hours of sunlight. Oops, I forgot the R. Part B, what is the minimum amount of daylight? What is the maximum? So again, I'm going to take, for my minimum, I'm going to take the sinusoidal axis and subtract the amplitude. And then for the max, I'm going to take the sinusoidal axis and add the amplitude. So for my minimum, I get 12 minus 2.4, which is 9.6. And then for my maximum, 12 plus 2.4, so 14.4. And those would be both hours of sunlight. Part C, what is the period? So again, 2 pi over b. Notice in this case, the b is still right after sine in front of the variable. So I'm going to take 2 pi divided by b, which in this case is 0.017. So I can do this directly on my calculator. So you do have a pi symbol. So again, it's above that exponent key. So 2, I'm going to do this in parentheses, I think, 2 pi divided by 0.017. So 369.6 roughly. So it's just about a full year. And part of that could be slightly off because of rounding. And then lastly, D, how many hours of daylight occur on day 350? So we would just be substituting this in for T. So you would take your equation. I'm going to type in exactly as I see it. And then instead of t, I'm going to put 350. Close out those parentheses, and then plus 12. So there's 9.6 hours on day 350. So that is all for applications. It really has a lot to do with your sinusoidal axis, amplitude, and finding that minimum and maximum. And then most questions you might see about the period or evaluating as well. So that's all for that. We'll review, and then we have our quiz or our test coming up shortly.